So omega is the same for everything, and that's why it's a useful quantity. Now the way to write it out in terms of its proper units is that omega is measured in radians per second. So if you're given something in revolutions per unit time, you have to multiply by 2 pi, because around each circle is 2 pi radians. For example, if you have something that goes at 1,000 RPM, which is typical for your car, and that means 1,000 revolutions per minute. To convert that to radians per second, you have to multiply by 1 revolution is 2 pi radians, and each minute is 60 seconds. So the conversion is like this. It's 1,000 radians times 2 pi divided by 60 seconds. In this case, it's 2,000 pi divided by 60 radians per second. You need to get at least into these units before you start plugging these numbers. So it's important that you're always using radians per second, because otherwise the quantity is meaningless. You cannot use revolutions per second. Once you have that, you can actually find the velocity. The velocity is simply just whatever this quantity is multiplied by the radius of how far the object is out from the sun. And you can see that it's very obvious that since this is the same for all objects, the velocity is linear proportional to the radius. If you're twice as far out, the velocity will be twice as large. And you can see that on these two bars, the velocity vectors are given by this green thing, this green vector. So I'm going to put this guy, I'll put him twice as far out as this guy. You can see his velocity vector is about twice as long as the inner vector. And that's because they have the same omega, but the radius is twice as much for the green one. Now I'm going to plug this back in here, and now I'm going to re-express this in terms of omega rather than velocity. And if I do that, then you get omega r all squared divided by r, which is this. So the acceleration is the angular acceleration, sorry, the angular velocity squared times the radius. And that's a proper dependence on r. You can also see that up here, in French process. This purple is so this purple or this pink letter is the acceleration vector. And the inner guy's 1 is shorter than this guy's. It's supposed to be half as much. You can see that in this equation because acceleration is linearly dependent on r. So if you double the radius, you're going to have double the acceleration. Now to go back to the problem at hand, the question is asking, so the purse is right here and the wallet was over here. The question was asking, what is the acceleration of the wallet? The magnitude of the acceleration of the wallet. We know the purse has acceleration, I think it was 2, 4. Yeah. Okay, so its acceleration is 2, 4. And I can easily use that to find its magnitude. Its magnitude is just the square of that. Square rooted, so it's 2 squared plus 4 squared, all square rooted. And I can actually use this formula now to find out what the angular acceleration, what the centripetal acceleration is of the wallet. So this equals omega squared times r of the purse. And that's just using that equation there. Now, why did I put that? Why did I put omega t? Why did I specify that?
Because it's the same.
It's the same for everything, so I don't need to specify that. I don't need to use different variables. And then likewise, for the wallet, it's also omega squared times the radius of the wallet. Okay. So there's 2 ways to do this. You can use this to solve for omega, and then plug that in here, and then solve for the acceleration. Or you can also write this as, I'm just going to rewrite this equation as omega squared equals acceleration divided by r. And I can rewrite this one also as omega squared equals acceleration divided by r. And because these are the same omega, I can set these things equal. And then you can just cross multiply this all. The take-home message from this problem was that you need to find some quantity that's the same for both of them, and you can determine that acceleration only depends on the radius. So if you know the acceleration and you know the radius, then you automatically know what omega is. And omega is the same everywhere, so you know how fast it's spinning. Once you know how fast it's spinning, you can find all the quantities. Given the radius. Yeah.
It's useful just to know that it's just going to be like whatever the, the magnitude is just going to be the ratio to the other one. So,
yeah,
I mean, so that's twice as much, so I'll just find the magnitude and then I'll just multiply it by 2. Is that useful or is it just?
Yeah, I mean, that's it actually, because it's, that's totally. Let me discuss this question of what about centrifugal acceleration. All right. So this question summarizes a lot of stuff. Question number 2. It says, which of the following correctly describes a particle moving with constant speed in a circular path? And then we will correct the answer. Number 1 is false, because the vector is changing direction. Number 2 is also false, because it's pointing inward. And you notice that at different points, inward is a different direction. If you're like this, then the vector's not constant. That's important that you recognize that these vectors are not constant, but the magnitudes may be. So when it says acceleration is constant magnitude, that is true. And the reason is because as long as you're not changing your radius, and this is the same, as long as you're not changing the radius, this is the same. This number is fixed. So acceleration is constant magnitude. The number 4th one says they're always perpendicular. This is true because on a circle, the radial direction is always perpendicular to the tangential direction. And A points inward radially and B points tangentially, so those are going to be equivalent. And the rest of them we can go through, they go along the lines of I think when I go on to the course, are there any questions on this question? Yeah. This is a pretty good question. So the question was, can I do number 66, chapter 4? Here's the question. It's on page 82 of your book if you want to follow along. The particle moves along a circular path at constant speed. At time t equals 4 seconds, it's at point 5,6. So it tells you what it is. So it's right there, at time t equals 4 seconds. And it has a velocity of 3 meters per second. Let me just make it hard this second. So at t equals 4 seconds, it has a position of 5,6. It has a velocity of 3j, which is the same thing as 0,3. And then it has an acceleration in the positive x direction. It doesn't give you the number, it just tells you which direction it is. The next thing it says is that at time 10 seconds, this is the second time, it has a velocity of negative 3 meters per second in the I direction, which is negative 3,0. and acceleration of positive y. The question is asking, what are the x and y coordinates of the center of the circular path? So let me just kind of plot this out a little bit. So at the beginning, it's starting right here, right? And we know directions of this thing is pointing. So let me draw these out. V again, I'll put in blue, and then I'll put the acceleration in orange. So at this point, its velocity is 0 to 3, so it's going up. And its acceleration points in the positive x direction. This, just knowing that itself should tell you which way this thing is rotating. You know the center has to be over here somewhere because it always points to the center, so it's kind of going. And then you know that 6 seconds later, we don't know where it is, but we know that its velocity vector is -3, 0. So just for illustration purposes, I know it should be over here somewhere. And I know its velocity vector has to be pointing in this direction, so I got to get the bottom of the circle. So I'll kind of just estimate it over here or something like that. It's going to be going like this. And the velocity vector points in that direction. And acceleration points in positive y. Well, that makes sense. It should be positive, pointing towards the center of the circle. We don't know exactly how big the circle is. That's the one thing that's tricky about this. But they do tell us that it took six seconds to get there. 6 seconds to get there. If I just draw this without the plane in the background. This thing did this. Just 6 seconds to get there. I can find omega using this information. Remember, omega is the key. Once you know omega, you can find all the other quantities because the only thing that depends on it is r. Okay, so I can find omega. How would I find omega? Again, omega is radians per second. And you know kind of it travels.
That was revolutions per second.
It's radians per second. It can be converted to revolutions per second. But it's proper units of radians per second. Okay?
It's gone 3/4 of the way around.
Okay, so stop. He said it went 3/4 of the circle. That's perfect. How many radians is that?
That is, it's 3 pi.
Okay, so it's 2 pi times 3/4. So its distance, it went, it's radians per second. So it went 2 pi times 3/4 of the circle, divided by 6 seconds. And that's it. That's omega. That's something. We need to find out how quickly it's rotating. We know exactly how many radians it went, and we know how long it took to go down. Yeah, Jerry.
Aren't you just assuming though that it went 3/4 of the quarter? Or 3/4 of the circle? Or do you-
Yeah, that's a good question. That assumption is correct. So he's asking, aren't you having an added assumption that it went 3/4? How do you know it went 3/4? Can somebody explain that? Why you know it's 3/4? Okay.
The velocity is the tangent line of the position, and since it's like perfectly clear, you can see that it's like that straight line is exactly at the bottom.
That's right. She's saying we know the velocity points in this direction, so we know we have to beat the bottom side. And over here, you know it's pointing up, so you know exactly where you are. Okay, so using this, we can find omega. And omega is, pi over 4 radians per second. Yeah. All right, so that's omega. And that's useful because now I can find the radius. We can use this formula that V equals omega r. Sorry, the magnitude of V equals omega r. And they give us magnitude of V is just 3. Keep in mind that this is uniform circular acceleration because the magnitude of V is always the same, at least from what we know so far. Here the magnitude is 3, here the magnitude is 3. In different directions, but the speed is still 3. So if I plug that in, I have 3 equals pi over 4 times r, which therefore equals 12 over pi. You may want to get a number for that. Let me just think of it. Did I do that?
Would you have to fund the coordinates?
Yeah, okay, that's right. So you get a decimal for that. Once you know the radius, you know it's going to be in that direction that much, so just add that to that coordinate and you can find the center of the circle. You good? Okay. Are there any questions on how I did that problem? Yeah, yeah.
I'm still not understanding how he came up with 3/4.
Oh, right here.
Yes.
We know that at the beginning it's at the left-hand side of the screen. So let me draw. We know it starts out right here. Is that clear why it does that?
Okay.
Because the velocity is pointing up. It has to be. We also know it ends over here. And this is 1, 2, 3/4 of a circle.
Yeah.
And the full is 2 pi, so I just took 2 pi. Are there any questions? So to recap, what I wanted to do here was to find omega, and here we know enough information about omega. Once you know omega, you can find the missing quantity here, which is odd. So let me go on to force. So force problems are an application of Newton's second law, second and third law. I think Professor Parr gave you guys a 10-step kind of recipe of solving problem. Many of those steps are going to do automatically in your mind. But physically, the most important steps that you need to be doing in all these problems, and I'm going to do them all in the ones I do in class, are draw a picture always. Invariably draw pictures all the time. Then use that picture to draw the free body diagrams. We'll talk about what those are. And the characteristics of a free body diagram is that every object should just be like a square. You don't have to like draw a nice pretty picture, just draw a square for the object. So it's simple to see where the forces are. Yeah, the square is some shape. Only label the forces. With their proper directions. Okay. And then next thing you want to do is you want to define your coordinate system. This is extremely important. And then from there you can go ahead and solve it. There's other steps that Professor Parr are important, but again, those are going to be more subconscious than the ones I'm discussing here. And so let me show you guys the importance of defining coordinate system. Don't get this guy. I'll give you guys some examples where, in one case, if you define the coordinate system badly, it'll make the problem extremely difficult. It won't make it unsolvable, but it'll make it much more fun. And then I'll give you another example where if you do define it properly, it'll make it much easier. So let's start out with a couple easy ones. And I'll take one from the online homework first to start out. Because this problem is actually basic, but it's tricking a lot of students because we're not going to have it yet. So this will be good practice. So the first problem is the online homework number 10. You can put it up on the board. And the question says, it's right up there. You got a 60-pound block on the floor, and somebody's trying to lift it by tying a rope to the top of that floor. And it tells you how much force is pulling away. The question is, what is the magnitude of the force exerted by the floor on the block? A simple picture would just look like this. There's this block, and there's this kid up here who's like trying to pull up on it. Okay? That's not the free body diagram, so I want to draw the free body diagram next, but just to get an idea. Free body diagram, you want to draw the free body that's in question, which is the block, nothing else. And then all the forces upon it. The forces are gravity, because it has a weight. The force that this kid is pulling upwards, which I call an F child. And then the last force is the normal force. The normal force is the force that whenever something is on a surface, the force pushes perpendicular to the surface so that the object doesn't go crashing into the surface. If that force didn't exist, the ball, everything that in this room would just go crashing into the earth. So the force keeps us so we don't go crashing. That force has to exist. It's called a normal force.
And
And it's called normal because it's normal or perpendicular to the surface.